8.7 Approximate Integration Part 1. We're going to talk today about the trapezoidal rule, and this video won't cover calculating error. I'll take that in Part 2. So, the trapezoidal rule is a way to approximate the area under the curve when you can't really do a definite integral. So first let's think about some times when it is impossible to get the exact value of a definite integral. And so we know why this is useful. The first example of when it's impossible to find the definite integral is when you can't find the antiderivative. When you have something like, let's say if you were integrating from 0 to 1 or from anything to anything else, from any a to b, e to the x squared dx. If you were trying to integrate this, you could look at u, du substitution. If you use u substitution and you say u equals x squared, then du would be 2x dx, and you don't have any other x in this problem to replace it with. So that's one instance when it'd be easier to approximate the area under the curve. Another instance is if your data comes from an experiment. If you just have a table of data and no function, I'm sure that you could work with the data to find a function, but that's hard and not in any way exact. So if your data comes from an experiment and you don't have the f of x, if you just have a table with x values and f of x values, then it is easier to approximate the area under the curve. So remembering that the integral equals the area under the curve, we've already approximated some integrals. We approximated using Riemann sums. Easy enough. A Riemann sum, an integral, is actually a limit of Riemann sums as your n approaches infinity. So a Riemann sum is from index 1 to n, f of x and any x from that subinterval, and then delta x times delta x. So we add up all these x's to find the Riemann sum. And remember, when we're finding Riemann sums, it's possible to find the left-hand sum within intervals. We use this notation, the left-hand sum within intervals, the right-hand sum within intervals. The left one, you'll be using the left endpoint of the interval. The right-hand sum, you use the right endpoint of the interval. And also the midpoint within intervals. So these just tell us what x we're choosing for our f of x all along the interval. So basically, what the trapezoidal rule does is it gives us another way to approximate the area under the curves by averaging the left-hand and right-hand Riemann sums using the left endpoint of the interval and the right endpoint of the interval. So let me draw a quick little curve. And say we wanted to find the area under this curve from A to B. And our n is 4. We got 4 intervals. If you're using the left hand, I'll do that in red. If you're using the left hand endpoint, your height comes from the left endpoint of the interval. So this one, this one, this one, and this one. You see how that leaves off the last point because you're using the left-hand part of that interval to find the height of that rectangle. So our rectangles, that one would zero out. Oops. Here's your height of the next rectangle. Oh, somehow I keep going over there. Here's your height of the last rectangle. That's with 4 intervals using the left-hand sums. Now I'll use a different color and do the right-hand sum, the right-hand endpoint of the interval. So the height of the first rectangle will be there. Height of the second rectangle. Height of the next rectangle. Somehow that one's a little more difficult for me to get exact. There we go. And the height of the last rectangle. So we're using this one, this one, this one, and this one. These endpoints to find our heights. Somehow it's hard to draw on here, but you get the idea. So the trapezoidal rule works by averaging the left and right. And you can see in the rule down here, now here's just your integral from a to b of f of x dx, approximated by the trapezoidal rule within intervals. And we remember delta x equals b minus a over n, just like it's always been. So we're using n intervals, and doing the trapezoidal rule, you'll take your delta x and divide it by 2. That accounts for the average. And the first endpoint and the last, or the first interval and the last interval, you're going to use that endpoint once. And all these middle ones are going to get multiplied by 2. Because if you're adding up the left and the right hands, you're going to use this one once when you're doing the left hand endpoints. You're going to use this one once when you're using the right hand endpoints. All these middle dudes are going to get used twice. So you see in this example, we're going to find the integral from 1 to 2 of 1 over x dx using the trapezoidal rule and the midpoint rule with n equal to 5. I divided up my little number line into intervals from 1 to 2 and using a delta x of 0.2, which I found my delta x. 2 minus 1 divided by 5 is 1/5 or 0.2. So I divided up my little intervals so I would know what my endpoints were. If I'm going to use the trapezoidal rule, I'm going to say 0.2, which is my delta x, over 2, times f of 1, take the first just once, and then f of 1.2, 1.4, 1.6, and 1.8. All of those get multiplied by 2, and my final point, f of 2, only gets used once. So you see, multiply all the middle ones by 2, and the first and last stay that way. Now f of 1 is going to be, we're using this f of x up here. Highlight my f of x for you. That f of x up there, 1 over x. So 1 over 1 is 1. 2 times 1 over 1.2, come from here. 2 times 1 over 1.4, etc. all the way through. Work that out. Pause the video if you need to. When you work that out, your answer will be approximately 0.69563.5-ish. Now let's do the same thing with the midpoint rule. If we look at our intervals, and this, again, 1.2, 1.4, 1.6, 1.8, and 2, the midpoints, if you've lined it all up right on the number line, the midpoints are pretty easy to see. 1.1, 1.3, 1.5, 1.7, and 1.9. So for the midpoint, I'm using my x's as midpoints of each interval. I've got 5 intervals, so 1, 2, 3, 4, 5 f of x's. I'm multiplying by delta x. It's just a plain old Riemann sum using the midpoints of the intervals. And again, it's the same f of x. So f of 1.1 is 1 over 1.1, 1 over 1.3, 1 over 1.5, etc., all the way through to the end. And the answer that you should get is about 0.691908. Now, if you evaluate it explicitly, that's why we picked, that's why we picked from 1 to 2 of 1 over x dx, because this is one that we actually can do the regular way, explicitly. If we evaluate this, it's going to be the natural log of x evaluated from 1 to 2, or the natural log of 2 minus the natural log of 1, which is 0. So the answer is going to be the natural log of 2. Which is 0.69314 and so on. So decide for yourself, which one's more accurate, the trapezoidal rule or the midpoint rule using 5 intervals. We'll discuss in the next video about finding this error, the upper limit for the error, and using other methods to approximate integrals.